Hello. So we were talking about the the sonar data, and I was talking about the figures. So here we have on the vertical axis what you see as deviance. Deviance is -2 times the log likelihood. So this is exactly almost like our L. And on the horizontal axis we have lambda. And then here we see this arrow going down and going up, going down and going up, going down and going up. And this is for penalized logistic regression. The sample size, excuse me, is 208 and number of features is 60, and ridge regression is presented here. This is elastic net B, and a C is a lasso. So one second. Okay, so first we read the data. I mean, first we do the first typical thing we call libraries, and then we read the data. So we have sonar, where we have columns 1 to 60 features, and then 61 is our response. Okay. Here we take the model matrix. Here we take the response. Here we turn the response into 1 and zeros. So Y currently is M and R, and then Y Y now turns into 1 and zeros. The sample size is the number of rows. Feature size is the number of 60 number of columns. Alpha elastic net, we set it to 0. M is 30. M is 30 means the number of lambdas we use from the smallest to the largest. And then we initialize the error of lasso ridge elastic net. So here we want to implement leave one out cross validation. Therefore, we will have a loop. This loop goes over individual observations, and we go over the ith one, store it in X test and Y test, and the rest into X train and Y train. Then we call the CVGLMnet function. What does CVGLMnet do? It does k-fold cross-validation for GLMnet, produces a plot, and returns a value for lambda. Okay. So actually I want to do something slightly different here. So okay, So I'm going to do something slightly different, and that's I'm just going to fit a generalized linear model cross-validation over to this data. So we use all the data, x and y. We make sure it is okay, so x and y binomial family, alpha equal 1 uh, makes this lasso. Let's just remove these. We say the number of folds is 5 and the type of measure is misclassification error. So let's just run this. Let's just ignore these. Okay. Now this lasso object has many things available. Dollar, the range of lambdas that were chosen, it was automatically chosen, or automatically finds a reasonable range of lambdas. If you're using Python, as far as I remember, you have to give it. There is no automatic option for you. So, and I will talk a little bit about how to find a reasonable range without if you don't have this option. So lasso CVM is the cross-validation error. Lasso N0 is the number of zeros in the coefficient vector as you reduce the lambda. You see, as you reduce the lambda is becoming smaller and smaller. The number of selected features increases. It starts from 0, goes to 1, 2, 3, 5, etc. So let's, and we can also plot this, plot this object lasso. Okay. So this object lasso here shows on the vertical axis this plot misclassification error, on the horizontal axis the log of lambda. This range is different for ridge and lasso, and on the top we see the number of selected variables for any lambda. So as lambda increases, the number of selected variables decreases, okay? And here you see the minimum lambda. So, the lambda that leads to the smallest misclassification error is indicated with this dashed line. And now what is this dashed line? This is something called as the one standard error rule. This one standard error rule says that since there is uncertainty around the cross-validation errors, and these error bars indicate that, therefore, even though this looks like the smallest, it may not be the smallest, because it could be anywhere from up here, from up here to below here. So this is the margin of error. So what it says is, okay, draw a line and find the first point on the right side for a larger lambda that reaches the same error. And that's the lambda. It's the lambda that is chosen by the one standard error. The rule of thumb is that because it chooses a larger lambda, we will select a simpler model that may perform better. In practice, I mean, even though it's part of the textbook, in practice, I have not seen necessarily improvement in the performance. I have not seen any evidence, but the idea is interesting, so I just want you guys to know, and you can access it here via lambda 1SC. We can also get the lambda that leads to the minimum cross-validation error here. Okay, so okay, C V plot. Okay, so this is the glmnet .stanford.edu. It shows how to use this, the glmnet package, which cvglmnet is a function of. And the nice thing is that you can have many great figures. For example, you can plot a fit. Let's do that. So this is CV lasso. This is glmnet. So plot lasso. So as the L1 norm increases, meaning as lambda decreases, the selected variables also, each of these colors refers to one of the 60 coefficients. So as the L1 norm increases, the number of selected variables also increase. Now, coming back to the CV lasso, once we run this cross-validation, we would like to fit the model with the lambda that leads to the smallest cross-validation error. So here we can just give lambda, and we say this lambda should be CV lasso. Let's run this again. Okay, CV lasso lambda min. Okay, so we are saying fit a glmnet with the lambda that leads to the smallest cross-validation error and hopefully to the smallest test error. And then now we have the coefficients. We have the intercept, and we have beta, and you can see that the second feature, the third feature haven't been selected. So they're clamped to 0 because they were deemed to be not strongly associated with the response. And so anyway, this is how you can see for the 60 features what is estimated, what is not. What is clamped to 0 and what is not. And total 22 variables were selected. Now we can do the same thing and have an LNet, elastic net. Although any number between 0 and 1 works, I just chose 0.5. Okay. Okay, so LNet more degrees of freedom. Why? Because there's a grouping effect probably happening. There are some of these features are strongly associated with the other features, but Lasso has clamped them to 0. ElasticNet won't do that. So let's just plot first minimum 1 standard error, 44 misclassification error. More variables are selected. Finally, we can do the same thing for ridge. For ridge, alpha is 0. K-fold. Say K is N. That will take longer. Okay, ridge. Okay. So plot CV ridge. It's all 60. Ridge does not clamp any variables to 0. And ridge, I have not ran this yet. So ridge, beta, you see all the variables are selected. Okay, so this is how we calculate how we perform cross validation, how we use the lambda that leads to minimum cross validation error, and to fit a GLM net. Now the question is, what if we don't know the range of lambdas? What I would do is I would create a sequence. Okay, so let's say LMB is a sequence from 2 to the power of a sequence. So sequence from negative 5 to 1. Okay, reasonable. then I would say, okay, fit this for this range, L and B. And then I would plot CV lasso. Okay, so let's just do this. Okay, so what do I see is that it goes down here and then it goes up and then it just saturates, right? So it shows that my upper limit of lambda is too big because I'm quickly near zero, no predictors. So I can reduce this. So I would probably start from -2 to -5. Let's try that. -5 to -2, sorry. So 1 second, sequence, 1, 2, 2, 10. Oh, I see. Let's see sequence. Okay. Okay, 1 to 10. Length out 100. Okay, that's what we want. We want to say how many points we want between these two, and that's our, let's say that's 30. You see, now it's much better. Now it's much better. I think we can still go below. So we can start with maybe -2. Let's go to -10, -4. Okay, so this is pretty low. All of it is pretty much the same. So I would make this maybe 6 to 2. Okay. So yeah, this looks better. This is the minimum we have here. Now I'm curious to see what would have happened if we wouldn't have. Let's go a little bit back. Make this 7 and make this 50. Okay, that's the minimum. Anyway, so you see, you don't have to rely on this. And a little bit playing with it allows you to find it. And now I just want to um, not use this, rely on the automatic version, and see how different it's going to be. So CV lasso. Okay, so CV lasso lambda min is this number. Now we run it without giving the range, and this figure will slightly change, but not fundamentally. It's taking time. It's taking forever, which is normal because it's cross validation. So one thing that will be part of the project will be to record this time automatically. You see now it's finished, and let's see what's the minimum. You see, not very different, and the graphs are not very different, and yeah. So anyway, um, this was just to show you how to implement lasso, um, essentially regularized logistic regression in R using the GLMNet package, and how to use cross-validation to find the optimal balance between model complexity and model fitness, okay, to avoid overfitting. And this was given in the context of the sonar data. We used lasso, ridge, and elastic net, and you also learned how to get the estimated coefficients. Okay, so if you're interested in the original paper that used this, this is the paper. If you just Google the name, it will come up, and it will give you in the introduction context of the data. It's a good example of how to talk about data, and how the signal is being represented. And here's an example of how the amplitude of a typical return would look different for a metal cylinder versus rock. And yeah, many other details. Anyway, I think I hope this example was useful in as an introduction to penalized logistic regression in general and cross-validation as well.